Hi, I'm Mr. Abdullah. This is part 2 of chapter 12, section 3. In this video, I'll be speaking about momentum. Actually, I will focus about the properties of momentum, but before I start with that, let's recall what we said about momentum in the previous video. First thing to start with is that momentum is the product of object's mass times its velocity. And we give them the momentum the symbol P small case. And its measuring unit is equal to kilogram multiplied meter over second. And this was the unit of the momentum. And momentum, we said that it describes the amount of motion caused by an object. So, or in other words, it is related to how much energy is actually given by a moving object in a certain direction. Let's say, for example, that one of your friends is running with a certain speed, with certain velocity in this direction, and that you were standing in his way. Once your friend actually reaches you, when your friend reaches your body, you will find that as soon as you collide, you'll find that you will be dropped down. You will drop down and fall to the ground. Actually, the idea is that your friend did not intentionally push you or imply a force on your body, even though your body was knocked down. So we say that your friend knocked you down because of his momentum. So because he was carrying certain energy in your direction, so you had to fall with the same direction in which he was moving. So when someone listens to this story, he would logically assumes or suggests that either your friend was moving with a really high speed so that he was able to knock you down, or that your friend is a bulky or massive guy. So the momentum describes a combination of how massive and how fast an object moves. So either your friend was really massive or that he was moving really fast. On the other hand, when you were actually standing in his way, your body did not want to move except when it was forced and it was acted on by your friend's momentum. So we say that your body had inertia. And inertia only describes how massive an object is. So inertia only describes how massive you actually are. So because your mass was not large enough, it could not hold on to your friend's momentum, and that's why you fell down to the ground. So in a quick comparison between inertia and momentum, anything that has mass actually has inertia, but not everything that has mass has momentum. It has to contain velocity, it has to be in motion. Other than that, it wouldn't have momentum. Let's move on to talking about the properties of momentum. The first property is that momentum is a vector quantity. And the word vector means that it includes direction. As we studied previously for the velocity, that when we call it a vector quantity, it means that velocity includes direction. The same case goes for momentum. Momentum is equal to mass times velocity. And since velocity has a direction, the momentum also have to have direction. The direction of the momentum will be the same as the direction of the velocity of the object. Now the second property is that the momentum can be changed by applying force. Now, how is that? First is if the force is in the same direction as the momentum, in this case, the momentum will be increased. Now, the second case, if the force is applied in the opposite direction, in this case, the momentum will decrease. And finally, if the force is applied in a different direction, in this case, the direction of the momentum will change. Let's have an example here. Let's say that you were standing and trying to push a box that is in front of you, and you're trying to push the box along this path. If you apply a force in this direction, in this way, you and the box will gain momentum in the same direction of the force. Now, as you keep applying the force for a longer time, the momentum will increase because you're applying the force in the same direction as the momentum. Meanwhile, let's say that the box is here now. Meanwhile, as the box is moving, it is being opposed by other forces. So other forces are acting on the box in the opposite direction, such as friction force and air resistance. So these forces are actually decreasing the momentum because they are acting in a direction opposite to the direction of the momentum. So when forces are applied in the opposite direction of the momentum will decrease. Now, in the third case, let's say that you have a friend that applied a force in a completely different direction from this direction, for example. So he applied a force while you're moving the box. He applied a force in this way. Right now, he will cause the box to move like that. The box will completely change the direction of its momentum. So the momentum of the box will change. It will move like that. So these are the three cases of applying forces. Either you apply the force in the same direction of the momentum, and this will increase the momentum, or you will apply the force in the opposite direction of the momentum, so the momentum will decrease, or the force will be applied from a different direction, and this will result to changing the direction of the momentum. This is property number 3, which states that the greater the momentum, the greater force or time required in order to stop the momentum or change its direction. And this explains why you can curve a baseball, for example, when throwing it with your hand, but you cannot curve a bullet when shooting it with a gun, because even though the bullet has much less mass than the baseball, it will have much greater momentum, and the reason is that the gun shoots the bullet with extremely high speed. Therefore, this will give the bullet a really large momentum, and this large momentum cannot be changed in a short period of time. You cannot change the direction of this momentum in a short period of time, or with a relatively small force by the curve of your hand. Unlike the ball, which has less momentum, so this could be possible. The next property that I will speak about is the conservation of momentum. And the word conservation means that the total momentum in an isolated system is actually constant, or it doesn't change. So let's speak, for instance, about the rocket propulsion. At first, when the rocket is at rest, and before the engine starts, the rocket will have zero momentum. Now, as soon as the engine starts, some gases will start being overheated inside the rocket. So there's a room here, or there's a space here that is called the combustion chamber. Inside this chamber, some gases start being heated, and when these gases overheat, they will expand until a point where the pressure will be so high, so these gases will be released downward. And as soon as these gases are released downward, then they will generate a momentum in this direction. They will generate a momentum in this direction. So we will have first a downward momentum due to the gases. According to Newton's third law, the gases' momentum will produce a reaction momentum. It will produce a reaction that is exactly equal in amount but opposite in direction. So this reaction momentum has to be in the upward direction. And this is actually the momentum that carries the rocket up in the sky. And this is the initial momentum before it all started. First, when the rocket was not moving, it had zero momentum. So even when it moved, the combination of all the momenta produced in this system has to equal zero. And speaking of the conservation of momentum, we also need to realize that the momentum is also conserved in collisions. When two objects collide with each other, the total momentum of the two objects before the collision will be exactly equal to the total momentum of the two objects after the collision. And this can be summarized by this equation, which says that P1 stands for the first object, the momentum of the first object, plus the momentum of the second object equal the two momenta after the collision. And this symbol, which is the asterisk, means that these momenta are actually after the collision. So let's take this for example, the Newton's cradle. If only one ball is moved from its position, when it actually collides with the other four balls, only one ball of these four will move in the same speed. And the reason is that the momentum that comes in, it will be the same as the momentum that comes out. If you notice in the same case, if you take two balls out and let them collide with the other three, only two balls of the other three will actually move out. So this is the same idea, that the momentum is conserved. So the number of balls that are moved in the first place, they will be the same number that comes out eventually. The next property to speak about is that the momentum can actually be transferred from one object to another during collisions, and this transfer will be either partially or completely. For applying the law of conservation of momentum, let's have a few examples here. Let's start with this one. It says, consider that the two cars in the diagram below colliding at the velocities shown. You have two cars, one blue and one red. These are the masses of the two cars. These are the masses, and these are the velocities. Okay, so this is the M and this is the V. It says if the two cars stick together after the collision and move as one unit, what will be the velocity of the combined cars after the collision? First thing we need to do is to find the total momentum before the collision. And this is, first we need to find the total momentum before the collision. And this is going to be equal to, first thing, the blue car is going to equal to the mass, which is 1.2, multiplied its velocity, which is 0.5, and this is equal to 0.6 kilogram times meter per second. And secondly, we need to calculate the momentum of the red car. So secondly, we need to calculate the red. So this is gonna be 1.4, the mass of the red car, multiplied by its velocity, which is 0.2. And now this will be 0.28 kilogram times meter per second. Now to sum up these two momenta are two vector quantities that have opposite directions. So you can't add them up, you need to subtract them. Why to subtract them? Because they are in opposite directions. This means that P total before the collision is equal to 0.6 minus 0.28, and this is gonna be equal to 0.32 kilogram times meter per second. So once we calculated the total momentum before the collision, this means that it is equal to the total momentum after the collision, and that's what the conservation of momentum law says. So after the collision, P is also gonna equal, P star is also gonna equal, P star total is also gonna equal 0.32 kilogram times meter per second. And the question says that there will be no two momenta after the collision because the two cars actually stuck together. So both cars has become one, as if it's one body or one unit moving together. So now all we're gonna do is say that the total momentum after the collision is gonna equal to both masses of the car, M of the blue car plus M of the red car, the total mass of the two cars multiplied by the velocity after the collision. This all is gonna equal 0.32, which is the momentum, the same momentum before the collision. Now the combined masses are 1.2 plus 1.4 multiplied V is gonna equal 0.32. So this means that V star will be equal to 0.32 divided by 2.6. And this is equal to 0.12 meter per second. Now to indicate the direction of this velocity, it has to be in the same direction of the greater momentum before the collision. And when these two vehicles collided, we found that the momentum of the blue car was greater than the momentum of the red car. So this means that after the collision, this motion or this velocity will be actually in the same direction of the blue car. So this is gonna be in the right direction. This is gonna be in the right direction. Let's check another example here where the momentum is partially transferred. It says that two snooker balls, A and B, each with a mass of 160 kilogram, collide with the velocities shown in the diagram. After the collision, the ball B travels right at 0.18. What will be the velocity of ball A after the collision, and indicate its direction? First thing you need to do is notice with me that the mass here is given in grams. So first you need to convert it to kilograms, and this is by dividing it, by 1000. So this is gonna equal 0.16 kilogram. Next thing to do is to apply the law of conservation of momentum. And first let's start by calculating the total momentum before the collision. So first we will calculate P total before the collision. This is gonna equal the mass times the velocity of the first ball minus the mass times the velocity of the second ball. And why minus, not plus? Because they are in opposite directions. Now the first mass is the same as the second, which is 0.16. This is multiplied by the first velocity, 0.28, minus 0.16 multiplied by 0.12. So the total momentum before the collision is gonna equal to 0.025 kilogram times meter per second. So this is the momentum before the collision. This is before collision. Now to find the momentum after the collision, the momentum P star, which means after the collision, the total momentum after the collision is going to equal to mass times V star, which means velocity after the collision for ball A, added to mass times velocity after the collision for ball B. The total momentum after the collision should be equal to the total momentum before the collision. So I'm gonna place here the number, which is 0.025. This should equal to the mass 0.16, the velocity after the collision for A, and this is what we want to calculate. So it's time V star A plus the mass is 0.16 times the velocity after the collision for B, which is given in the question right there. It's 0.18. This means that V star A is gonna equal zero 0.025 minus 0.028 divided by 0.16. If you finish up the calculations, you'll find that the V star for A is gonna equal minus 0.02 meter per second. Now the negative value for the velocity of ball A after the collision, it means that it moved in oppositely to how it was moving in the before the collision. So this means that before the collision it was moving right. Then this means that after the collision, the ball V, its velocity will be to the left. It will be exactly like that. So this means that velocity A, the direction of this velocity is going to be to the left. Okay, now one more question which discusses a complete transfer of momentum. Here it says a billiard cue ball accelerates from rest at a rate of 0.6 meter per second squared for continuous 4 seconds. If the mass of the cue ball is 0.17 kilogram, what is the momentum of the ball after 4 seconds? The problem here is when you want to find the momentum of the ball is equal to m times v, and you don't have the velocity. You don't here have the velocity. You have acceleration and time. So first thing you need to do is to apply the acceleration rule to find the velocity. And this rule says that A, acceleration, is equal to v2 minus v1 over t. Now v2, to find v2, it's going to be equal to A times t plus v1. A is 0.6, the time is 4 seconds, and v1 starts from rest, which means that v1 is equal 0. So it's plus 0. This means that v2 is equal to 2.4 meter per second. So now after we found v2, we said that it's equal to 2.4 meter per second. All we need to do is to find the momentum. The momentum is going to be equal P mass times V. The mass of the cue ball is 0.17. The velocity or the speed is 2.4. This means that the momentum will be equal to 0.4 kilogram times meter per second. So this is how we solve I. So I just solved I. Now let's move on to double I. Let's move on to solving double I. It says that after these 4 seconds, the ball hits another one whose mass is 0.12 kilogram, and this ball is at rest. What is the velocity by which the second ball will move after the collision in case the momentum is completely transferred? So here the question assumes that the momentum is completely transferred. This means that the total momentum before the collision, it was m times v for the cue ball plus m times v for the second ball. Now to start with, it says that the second ball was at rest at first. This means that it will have no momentum, so this will be equal to 0. So while the momentum before the collision we just calculated from number I. So the total momentum before the collision will be equal to 0.4 plus 0, and this is equal to 0.4. So this is the total momentum before the collision. This is before the collision. Now P star, the total momentum after the collision, should be equal to the same momentum before the collision. So it should be equal to 0.4. But now, after the momentum is completely transferred, this means that the cue ball will come to rest while the second ball will move, because all the momentum of the cue ball has moved to the second ball. So logically, now m times v star for the cue ball should be equal 0. And we need to find the mass times v star for the second ball. Here, all what we don't have is the v star, which is the velocity of the second ball after the collision. And how can we find that? The total momentum after the collision is exactly equal to before the collision, which was 0.4. So this equation is gonna be summarized as 0.4 equal 0 plus the mass of the second ball, which is 0.12, okay, multiplied v star. Now this means that v star is equal to 0.4 divided by 0.12, and this is equal to 3.33 meter per second. So this is the velocity of the second ball after the collision. Okay, so those were multiple examples that show how can you use the law of conservation of momentum in the problems or in the equations. I hope that was helpful. See you on the next video.